The universe is a mysterious place, filled with wonders that stretch the limits of our understanding. Beyond the stars and galaxies visible to the naked eye, there are phenomena so strange and baffling that they challenge the very laws of physics. Join me as we explore these peculiar occurrences. From planets that defy gravity and stars that seem to cheat time, to vast empty voids and fleeting moments too brief to measure, the cosmos is full of strange phenomena, some of which remain yet to be solved. Fomalhaut b, the Vanishing Exoplanet. In 2008, astronomers made a remarkable discovery near the bright star Fomalhaut, which is located about 25 light-years away from Earth. Using the Hubble Space Telescope, they identified what appeared to be a planet orbiting this star. This was no ordinary planet. It was one of the first exoplanets ever detected by direct imaging, a method that involves taking a picture of the planet itself, rather than detecting it through the gravitational influence it has on its parent star, or through the dimming of starlight as it passes in front of it. The newly discovered planet was named Fomalhaut b, and it was heralded as a significant breakthrough in our ability to study planets outside our solar system. But then, something strange happened. In subsequent years, as astronomers continued to observe Fomalhaut and its surroundings, the planet seemed to vanish. Fomalhaut b was no longer detectable. It had simply disappeared. This vanishing act puzzled scientists. How could a planet, large enough to be seen from across space, just cease to exist in the span of a few years? Some began to question whether Fomalhaut b had ever been a planet at all. Perhaps the original detection was an error, or maybe it was not a solid object like a planet, but rather a cloud of dust or debris. The more scientists looked, the more uncertain the situation became. One of the leading theories to explain Fomalhaut b's disappearance is that it was never a planet in the first place, but rather the aftermath of a colossal collision between two icy bodies orbiting Fomalhaut. Such a collision would have generated a large cloud of dust and debris, which could have been mistaken for a planet when first observed in 2008. Over time, this cloud would have dispersed, becoming too thin to be detected by our telescopes. In this scenario, Fomalhaut b was not a planet that vanished, but the debris from a cosmic accident that only briefly appeared as a planet-like object. But this explanation, while plausible, doesn't satisfy everyone. There are still questions about what exactly happened. Could it be that Fomalhaut b was a real planet, and that something more mysterious occurred to cause its disappearance? Some researchers have speculated that the planet may have been destroyed in a violent event, perhaps involving a collision with another large object, or the gravitational forces of Fomalhaut itself tearing the planet apart. If Fomalhaut b had been shattered in such a cataclysmic event, the debris could have dispersed rapidly, explaining why it no longer appears in our observations. Others suggest that our instruments may have been misleading us from the start. Observing distant planets is a complex process, and the data we receive is often fragmentary. It is possible that what we interpreted as a planet in 2008 was something else entirely. Perhaps a transient phenomenon, like a dust storm, or a gas cloud that happened to look planet-like in that moment. As our technology improves and our understanding of space deepens, we may one day uncover more about what we were actually seeing. This leads us to a broader question. Does the universe deliberately hide its truths from us? Or are we simply misinterpreting the fragments we can observe? In the case of Fomalhaut b, we are left with only a partial understanding. We saw something, but what exactly we saw remains uncertain. The universe, vast and complex, often reveals itself to us in pieces, and it is up to us to put those pieces together. But the universe is not always forthcoming. Astronomers must rely on the data they can gather from distant points of light, and from this data, they must infer the existence of planets, stars, and other celestial phenomena. It is a challenging task, one that requires not only technological precision, but also interpretative skill. And sometimes, as with Fomalhaut b, the pieces of the puzzle do not fit neatly together. In many ways, the story of Fomalhaut b is a reminder of how much we still don't know. Despite our best efforts and our most advanced tools, the universe continues to surprise us, presenting mysteries that challenge our understanding. Planets that disappear, signals that defy explanation, phenomena that come and go without a clear cause. All of these remind us of the limitations of human knowledge and the complexities of the cosmos. The disappearance of Fomalhaut b could be seen as a metaphor for our broader quest to understand the universe. We catch glimpses of the truth, but that truth is often fleeting, hidden behind layers of uncertainty and ambiguity. As we peer deeper into space, we uncover new information, but each discovery seems to raise more questions than it answers. Is the universe deliberately elusive, revealing itself in fragments? Or are we simply not equipped to grasp its full reality? The debate over what happened to Fomalhaut b continues, with new observations and theories emerging over time. Yet even if we never fully solve the mystery of this vanishing exoplanet, the search for answers will undoubtedly lead to new insights into the nature of the universe. Each puzzle we encounter, each fragment of reality that we struggle to interpret, pushes the boundaries of our knowledge just a little further. Dark Galaxy Dragonfly 44. In 2016, astronomers made a discovery that added yet another layer of mystery to our understanding of the universe. They found a galaxy named Dragonfly 44 that behaves unlike any other galaxy we have studied. What makes Dragonfly 44 so extraordinary is that almost none of its mass is made up of the usual components we expect to find in galaxies: stars, gas, and dust. In fact, less than 0.01% of the galaxy's mass consists of visible matter. The rest, a staggering 99%, appears to be made of dark matter, an invisible and elusive substance that has perplexed scientists for decades. Dark matter, as far as we know, does not emit, absorb, or reflect light, making it impossible to detect directly. It's a mysterious form of matter that we infer from the gravitational effects it has on galaxies and other objects in the universe. We know it must exist because the gravitational pull we observe in galaxies is far stronger than the visible matter alone could produce. In other words, something unseen is holding these galaxies together, and that something is what we call dark matter. Dragonfly 44 is an extreme example of this. Unlike most galaxies, which have large, bright clusters of stars at their centers and throughout their spiral arms, Dragonfly 44 has very few stars. Its light is dim, and to the naked eye, it would appear almost as a shadow against the backdrop of space. Despite this, the galaxy behaves as though it is held together by an enormous amount of mass, far more than can be accounted for by its stars or gas. The only explanation is that the vast majority of its mass must come from dark matter. This ghostly galaxy has forced astronomers to reconsider some of their assumptions about how galaxies form and behave. In most cases, it is the gravitational pull of stars and gas that gives a galaxy its structure and stability. But in Dragonfly 44, with so few stars, it's unclear how the galaxy remains held together. The dark matter, which we cannot see or directly interact with, must be playing an unusually central role in shaping the galaxy's form and keeping it from dispersing into space. The discovery of Dragonfly 44 raises important questions about the role dark matter plays in the universe. While we already knew that dark matter is a key component of most galaxies, we never expected to find a galaxy like Dragonfly 44 where visible matter is so minimal. This suggests that dark matter may not just be a hidden background force in the cosmos, but could also be the primary framework around which some galaxies are built. This shifts the way we think about the universe's structure. If a galaxy like Dragonfly 44 can exist with almost no visible matter, it implies that dark matter is not just a passive player, but an active, fundamental component in the formation of some galaxies. This challenges the traditional models of galaxy formation, which emphasize the importance of stars, gas, and dust in creating the gravitational forces necessary to shape a galaxy. With Dragonfly 44, dark matter seems to have taken on that role almost entirely by itself. Yet dark matter remains a mystery. We do not know what it is made of, and so far, it has eluded every attempt to directly detect it. We know that it must interact with regular matter through gravity, but beyond that, its properties remain unknown. Galaxies like Dragonfly 44 remind us of how much we have yet to learn. It is as though we are observing the universe through a fog, only catching glimpses of the underlying structure, while much of the true nature of reality remains obscured. The discovery of Dragonfly 44 also sparks philosophical questions about the nature of the universe and the limits of human understanding. We have long assumed that the universe's visible elements, stars, planets, gas clouds, and galaxies, were the key components of cosmic structure. But Dragonfly 44 suggests that the visible universe may be only a fraction of the full picture. If dark matter can create and sustain entire galaxies with almost no contribution from visible matter, how much of the universe's true architecture are we missing? Are there other forces at play that we have yet to discover? Or does dark matter itself hold secrets that could reshape our understanding of existence? Some scientists even wonder if dark matter could be connected to other unsolved mysteries in physics, such as the nature of gravity or the origins of the universe. If we can one day understand dark matter, it might offer answers to questions that have eluded us for centuries. Yet for now, Dragonfly 44 stands as a silent enigma, a galaxy that defies our expectations and challenges our comprehension of the cosmos. The galaxy's name, Dragonfly 44, is fitting in its own way. Like a dragonfly, it is delicate and elusive, almost invisible in the grand scheme of the universe, yet it is bound together by forces we cannot see. It is a reminder that the universe is far more complex than it appears, and that we are only beginning to peel back the layers of the unknown. Dark matter, once considered a marginal player in the universe, is now seen as a potential key to understanding the very fabric of reality. Quantum fluctuations in a vacuum. In space, where the human eye perceives emptiness, lies a hidden reality far stranger than we can imagine. What seems to be void and silence, even in the most desolate corners of the universe, is not actually empty at all. It is a space brimming with constant activity, although it remains invisible to us. This phenomenon is a product of quantum theory, a branch of physics that describes the universe at its most fundamental level. And what it reveals is both mind-boggling and humbling. The notion that even in a vacuum, where there is supposedly nothing, something is happening. Quantum fluctuations are tiny, momentary changes in energy that occur even in what we call empty space. These fluctuations aren't merely theoretical, they are real, though they happen on a scale so small and brief that they defy everyday understanding. Particles, some so small they cannot be seen or detected by current technology, appear and vanish in the blink of an eye. They flicker into existence, last for an instant, and then disappear again. It is a strange concept to grasp. After all, how can particles emerge from nothing and then simply vanish? To our everyday experiences, this seems impossible. But quantum physics doesn't operate by the rules we observe in the world around us. On this microscopic level, uncertainty reigns. The particles that briefly appear in these quantum fluctuations do not obey the familiar laws of Newtonian physics. Instead, they exist in a world of probabilities, where things can happen without an apparent cause or origin. This peculiar activity has led scientists to describe space, even in a vacuum, as something that is far from empty. It is more like a bubbling pot of potential, where particles pop into and out of existence in ways that are unpredictable and seemingly random. These fluctuations, though fleeting, have real effects. They generate small bursts of energy, so minute that detecting them requires advanced equipment and highly sensitive experiments. Yet they hold the potential to influence much larger events in the universe. Some scientists propose that these tiny fluctuations may even help explain why the universe is expanding. For decades, researchers have puzzled over the mysterious force known as dark energy, which is believed to drive the accelerated expansion of the universe. Quantum fluctuations could, in theory, contribute to this force, providing the small pushes needed to propel galaxies away from each other over time. It's an idea that remains under exploration, but the possibility is there, that the universe's expansion may have its roots in these quantum hiccups happening all around us, in places we would consider empty. Even more astonishing is the idea that quantum fluctuations might give rise to entire universes. This brings us into the realm of speculative physics and cosmology, but it's a concept that some leading scientists take seriously. In a multiverse theory, where our universe is just one of many, new universes could be constantly born from these fluctuations. The idea suggests that in the vast, empty space beyond our observable universe, quantum activity could eventually spark the creation of entirely new realms, complete with their own stars, galaxies, and even laws of physics. The notion that something could come from nothing is deeply counterintuitive, yet quantum fluctuations force us to reconsider our assumptions about what nothing really means. In classical terms, nothingness implies the absence of everything. No matter, no energy, no space, no time. But quantum physics shows us that even in the absence of matter and energy, space itself has an underlying structure. The fabric of space-time is not flat or empty, but filled with potential, always on the verge of bringing forth new particles and energy bursts, no matter how fleeting they are. This raises a philosophical question as old as human curiosity itself. Can something truly come from nothing? Quantum fluctuations seem to suggest that the answer is yes, at least on the smallest scale. But this leads to an even more profound inquiry. Is nothingness itself an illusion? If even the most empty parts of the universe are active, teeming with energy and particles that appear out of nowhere, then perhaps the very concept of emptiness is flawed. Perhaps what we consider to be nothing is in fact filled with the seeds of creation. The implications of this question extend beyond science and into the realm of philosophy and metaphysics. For centuries, thinkers have debated the nature of existence and whether it is possible for something to arise from pure nothingness. Quantum fluctuations provide a glimpse into a reality where this may indeed be possible, challenging long-held notions about the universe and the nature of existence itself. In this strange dance of particles and energy, the universe itself could be echoing a deeper truth, that the line between something and nothing is far blurrier than we ever thought. Oumuamua, the Interstellar Visitor. In 2017, an object unlike anything astronomers had ever seen entered our solar system. It came from beyond our planetary neighborhood, moving at a speed too great for it to have originated within the solar system itself. Named Oumuamua, a Hawaiian term meaning scout or messenger from afar, this elongated cigar-shaped object quickly captured the attention of scientists and the public alike. Its visit marked the first time humans had ever observed an interstellar object passing through our solar system, and with it came a host of mysteries that remain unresolved. Oumuamua's shape was the first thing that set it apart. Most asteroids and comets that we are familiar with tend to be roughly spherical or irregular in shape, but Oumuamua was long and narrow, resembling a cigar, or perhaps even a flattened pancake. This unusual shape was unlike anything seen before, and it immediately raised questions about the object's origins. It didn't fit neatly into any of the categories astronomers use to classify objects in space, and that was just the beginning of the puzzle. As Oumuamua passed through the solar system, astronomers noticed something else unusual. It didn't behave like a comet or an asteroid. Comets, which are made of ice and rock, tend to develop a glowing coma and tail as they get close to the sun. This is because the heat from the sun causes the ice to vaporize, creating a trail of gas and dust that follows the comet. But Oumuamua showed no such behavior. There was no visible tail, no signs of outgassing, nothing to suggest it was a typical comet. Yet its motion was peculiar. As it approached the sun, its trajectory was what scientists expected, following a path governed by the sun's gravity. But after it passed the sun and began moving away, something unexpected happened. It accelerated. This acceleration was small, but it was enough to baffle astronomers. Without any evidence of outgassing or the typical signs of a comet, there was no clear explanation for why Oumuamua would speed up as it left the solar system. Gravity alone couldn't account for the change in its velocity, and with no visible means of propulsion, the object's behavior sparked intense debate in the scientific community. One of the leading theories suggests that Oumuamua could be a fragment of a planet that was destroyed in another star system. In this scenario, the object could be a shard of a rocky planet that was torn apart by gravitational forces, leaving it elongated and tumbling through space. Over time, it may have traveled across interstellar space, eventually making its way to our solar system by chance. This theory explains its unusual shape, but it doesn't account for the acceleration observed as Oumuamua left the Sun's influence. Another possibility is that Oumuamua is covered in a layer of hydrogen ice, which would sublimate, turn from solid to gas, as it approached the Sun, providing the additional push needed to explain its acceleration. But this theory also has its problems. The absence of visible outgassing remains a sticking point, and hydrogen ice is not something we have observed in this form before. Yet there is another, more speculative idea that has captured the imaginations of some scientists and the public alike. What if Oumuamua is not a natural object at all? Could it be an artificial object, perhaps a probe or a piece of technology from another civilization? This idea, while far from the mainstream, was seriously proposed by some researchers, including well-known Harvard astronomer Avi Loeb. Loeb and others suggested that the object's unusual acceleration could be the result of some form of propulsion or design rather than a natural phenomenon. The idea that Oumuamua could be an alien probe is intriguing because it raises the possibility that we are not alone in the universe. If an object from another star system can pass through our solar system, what else might be out there, waiting to be discovered? However, most astronomers remain cautious about this theory. There is no direct evidence to suggest that Oumuamua is anything other than a natural object, and the lack of radio signals or any other signs of technology makes the alien hypothesis speculative at best. Whatever its true nature, Oumuamua has reminded us of how little we know about the universe beyond our solar system. The object's brief visit, lasting only a few weeks before it moved out of range of our telescopes, gave scientists only a limited window to study it. Despite the intense scrutiny it received during that time, many questions remain unanswered. Where did it come from? What forces shaped it? And why did it behave the way it did? The Bootes Void. In the universe filled with countless stars, galaxies, and clusters of cosmic material, there exists a region so empty and so devoid of matter that it stands out as an enigma. This region is known as the Bootes Void, one of the largest voids in the known universe, and it stretches across an astonishing 700 million light-years. For a long time, its sheer emptiness baffled astronomers. While voids are not uncommon in the cosmic web, the Bootes Void is extraordinary in both its size and its lack of galaxies, raising profound questions about how the universe is structured. When astronomers first mapped this region in the constellation of Bootes, they were struck by its apparent emptiness. In a universe filled with clusters of galaxies, star systems, and dark matter, the Bootes Void appeared almost as if it were an anomaly, a vast cosmic desert where galaxies are few and far between. Within this immense volume of space, only a handful of galaxies have been detected, far fewer than one would expect given its size. This emptiness led some scientists to speculate whether the void could be the result of unknown forces, or perhaps even an artificial creation. Could there be something about this region of space that prevents galaxies from forming, or has something in the distant past swept them away? Most of space, at least as we perceive it, is made up of vast expanses of nothingness. Galaxies are scattered throughout the cosmos like islands in a dark sea, connected by invisible filaments of dark matter and energy. But even in these empty regions, the Bootes Void stands out. Compared to other voids, it is immense and curiously barren, with so few galaxies that some astronomers began to wonder if it operated under different laws of physics. Yet, as we continue to study the void, its existence offers important clues about the formation of large-scale structures in the universe. The Bute's void challenges our understanding of cosmic evolution. Galaxies typically form within dense regions of space, pulled together by gravity, and over time, clusters of galaxies merge and grow. In areas where matter is sparse, galaxies still form, albeit at a slower rate. But in the Bute's void, this process seems to have been dramatically curtailed. Some researchers believe that the void could be the result of several smaller voids merging over billions of years, gradually expanding to create one of the largest known empty regions in the cosmos. But even this explanation leaves questions unanswered. Why is the void so large? And why does it contain so few galaxies, even by void standards? One possible explanation for the Bute's void lies in the early history of the universe. After the Big Bang, matter was not evenly distributed throughout space. Over time, areas of higher density began to collapse under their own gravity, forming galaxies and clusters, while less dense regions became increasingly empty. The Bute's void could be one such region where the density was simply too low for galaxies to form in significant numbers. But if this is the case, it still does not explain why this particular void is so much larger and emptier than others. Another possibility is that the Bute's void is the result of a large-scale cosmic event that swept the region clean of galaxies. Some researchers have speculated that interactions between galaxies, such as collisions or mergers, could have caused the void to form, with the resulting gravitational forces pulling galaxies out of the area over time. Alternatively, the void may have formed as part of the natural ebb and flow of cosmic evolution, with galaxies gradually migrating toward denser regions, leaving behind a vast empty space. When we look at this enormous cosmic whole, we cannot help but wonder, does emptiness have a purpose, or is it simply the absence of structure and meaning? Is the void a necessary part of the universe's design, or is it simply a random occurrence, a byproduct of the way matter has distributed itself across space? On Earth, emptiness is often associated with absence, a lack of something, be it matter, energy, or meaning. But in the vast reaches of space, emptiness is a fundamental part of the universe's structure. Without voids, the galaxies that populate the universe might not exist in the same way. These vast empty regions create the space in which matter can cluster and form the galaxies, stars, and planets we observe today. Without voids, the cosmic web, with its intricate filaments of dark matter and clusters of galaxies, might not have developed in the way it has. Yet, despite the important role voids play in shaping the universe, the Bute's void is so extreme in its emptiness that it stands apart. Its sheer size and lack of galaxies raise questions about the forces that govern the cosmos. Could it be that in this region of space, different rules apply? Or is the void simply an extreme example of a phenomenon that occurs throughout the universe? Planets with impossible orbits. In the search for planets beyond our solar system, astronomers have uncovered a wide variety of strange and fascinating worlds. Among these discoveries, some exoplanets stand out because they seem to defy the very laws of physics. These are planets that exist in conditions so extreme, so seemingly impossible, that scientists are left questioning what they thought they knew about how planets form and survive. These so-called impossible planets orbit their stars in ways that contradict established models, presenting challenges that have yet to be fully explained. One of the most striking examples of this is WASP 18b, a planet that orbits so close to its star that by all accounts it should have been destroyed long ago. WASP 18b is a gas giant similar in size to Jupiter, but its proximity to its star is far more extreme. It completes an orbit in less than 24 hours, which means it is located at an extraordinarily short distance from its star, just 1.9 million miles away, far closer than Mercury is to our Sun. This close proximity causes immense tidal forces between the planet and the star. forces that should have either caused the planet to spiral inward and be consumed by its star, or ripped it apart entirely. Yet, there it is, defying expectations. WASP-18. B's existence forces astronomers to reconsider their understanding of tidal interactions, the gravitational forces that occur between a star and a planet. According to current models, the gravitational pull between a planet and its star should cause the planet's orbit to decay over time, slowly pulling it closer until it is eventually consumed by the star. But WASP-18b has apparently managed to survive in this precarious position, suggesting that something about its interactions with its star is different from what we expected. Some scientists speculate that the planet's internal structure or its atmosphere might be playing a role in its survival, but for now, WASP-18b remains a mystery. There are other exoplanets that also seem to defy our understanding of how planets behave in their orbits. Some of these planets orbit their stars in the opposite direction of the star's rotation, a phenomenon known as a retrograde orbit. In our solar system, all of the planets orbit in the same direction as the Sun's rotation, a consequence of the way the solar system formed from a rotating disk of gas and dust. But in other star systems, planets like HAT P7b and WASP-17b orbit in the opposite direction, as if they are swimming upstream against the natural flow of the system. This type of orbit contradicts the conventional model of planetary formation, which suggests that planets should form and orbit in the same direction as the rotating disk of material from which they originated. One possible explanation for these retrograde orbits is that the planets were affected by gravitational interactions with other objects in their star system. These interactions, known as gravitational perturbations, could have caused the planets to shift into retrograde orbits over time. For instance, a close encounter with another massive object, such as a nearby planet or star, could have thrown the planet off its original course and reversed its orbit. However, this still leaves questions about how such dramatic changes could occur without destabilizing the planet's orbit entirely. Retrograde planets like WASP-17b challenge our understanding of the forces that govern planetary motion. Then, there are planets with orbits so tight that they defy the natural life expectancy of a planet in such extreme conditions. These so-called hot Jupiters are gas giants that orbit their stars at such close distances that they are heated to scorching temperatures. Some of these planets, such as Kepler-78b, orbit so closely to their stars that they complete an entire orbit in just a few hours. The heat and radiation from the star should strip away the planet's atmosphere and cause it to disintegrate, yet these planets persist, enduring conditions that should be lethal for any known form of planetary life. Kepler-78b, for instance, is a rocky planet about the size of Earth, but it orbits so close to its star that its surface temperatures likely reach over 2,000 degrees Celsius. At such temperatures, the planet's surface could be molten, and its orbit is so tight that it should be spiraling toward its star at a rapid pace. According to existing models, planets in such tight orbits should have relatively short lifespans. Yet, Kepler-78b continues to exist in its precarious orbit, forcing scientists to rethink how long planets can survive under such extreme conditions. These impossible planets raise profound questions about the nature of planetary formation and survival. Our current models of how planets form and evolve are based on observations of our own solar system, but exoplanets like WASP-18b, HAT P7b, and Kepler-78b suggest that the universe is far more diverse and unpredictable than we once thought. These planets exist in environments that seem hostile to their survival, yet they persist, defying the forces that should have destroyed them long ago. The discovery of these exoplanets has sparked new avenues of research as scientists work to understand how such planets can exist. Some researchers are exploring the possibility that these planets formed in a different way from the planets in our solar system. For example, it's possible that some of these impossible planets formed farther away from their stars and then migrated inward over time. This migration could explain how planets like WASP-18b ended up in such close orbits without being consumed by their stars. However, this theory is still being tested, and many questions remain. Other scientists are exploring the possibility that the physical properties of these planets, such as their atmospheres, magnetic fields, or internal structures, might be different from what we expect. These factors could help explain why some planets are able to survive in extreme conditions. For instance, if a planet like WASP-18b has a particularly strong magnetic field or a dense atmosphere, it might be able to withstand the intense tidal forces exerted by its star. But again, these are just theories, and much more research is needed to fully understand these strange and seemingly impossible worlds. Ultimately, the discovery of exoplanets with impossible orbits highlights the limits of our current knowledge. While we have made incredible strides in understanding how planets form and evolve, the universe continues to surprise us with new discoveries that challenge our assumptions. These planets exist on the edge of what we consider possible, pushing the boundaries of our understanding and forcing us to reconsider the fundamental principles of planetary science. The Idenus Supervoid. In the universe, there are places where galaxies cluster together, where stars are born in great clouds of gas, and where the pull of gravity weaves matter into intricate patterns across the cosmos. But then, there are places like the Idenus Supervoid, a region so empty and so vast that it stretches our understanding of the universe's structure. Spanning nearly 1 billion light-years, the Idenus Supervoid is one of the largest known voids in the universe, a cold, desolate expanse where almost nothing seems to exist. Its size and emptiness have puzzled astronomers for years, as it doesn't fit neatly into the models of how the universe is supposed to be distributed. Most voids in the universe are relatively small pockets of space where the density of galaxies and matter is lower than average. These voids are common, and they form naturally in the cosmic web, the large-scale structure of the universe where matter is clumped together in long filaments and sheets, leaving behind pockets of emptiness. But the Idenus Supervoid is different. It is far larger than typical voids, stretching across nearly 1 billion light-years of space. This makes it unusually vast, even by cosmic standards. The question is, why? What could cause such a large region of space to be so devoid of galaxies, stars, and other matter? The Idenus Supervoid was first detected when astronomers noticed an unusual feature in the cosmic microwave background, CMB, the faint glow of radiation left over from the Big Bang. This radiation is spread almost evenly across the sky, but there are small fluctuations in temperature that tell us about the early conditions of the universe. In the direction of the Idenus constellation, however, astronomers found a large, unusually cold spot in the CMB. This cold spot caught their attention because it didn't seem to fit with the expected variations in the cosmic microwave background. Further investigation revealed that this cold spot aligned with a vast, empty region of space, the Idenus Supervoid. This void is colder than other parts of the universe, and the temperature difference is not insignificant. It's as though this region of space is missing something: matter, energy, and warmth, all of which are present in greater abundance elsewhere in the universe. But why is this region so different? What could cause such an enormous stretch of space to be so empty and cold? One theory is that the Idenus Supervoid is simply an unusually large void, a region that formed naturally as part of the universe's evolution. After the Big Bang, matter wasn't evenly distributed throughout space. Over time, gravitational forces caused some regions to become more dense, forming galaxies and clusters, while other regions became more empty. The Idenus Supervoid could be one of these empty regions, a cosmic desert left behind as matter clumped together elsewhere. But even this explanation doesn't fully account for the void's size and temperature, leaving astronomers searching for alternative ideas. A more speculative theory suggests that the Idenus Supervoid might be the result of something far stranger: the influence of a parallel universe. Some scientists have proposed that the void could be the result of a gravitational pull from another universe, tugging at the matter in our own universe and creating a region of space that is unusually empty. This idea comes from the theory of the multiverse, which suggests that our universe might be just one of many, each existing in its own separate reality. If a parallel universe were close enough to ours, its gravitational influence could affect the distribution of matter in our universe, potentially creating large voids like the one in Eridanus. This idea is still highly speculative, and there is no direct evidence to support the existence of parallel universes. However, the Eridanus Supervoid is so unusual that some researchers are willing to entertain the possibility that it might be the result of interactions with another universe. If this were the case, it would represent a profound shift in our understanding of reality, suggesting that the universe we live in is not the only one, but part of a larger, interconnected multiverse. While the idea of parallel universes might sound like science fiction, the Eridanus Supervoid continues to challenge our understanding of how the universe works. Its size, coldness, and emptiness raise questions that current models of cosmic evolution struggle to answer. If the void is not the result of gravitational forces from a parallel universe, then what could have caused such an extreme feature in the cosmic landscape? Some researchers have proposed that dark energy, the mysterious force driving the accelerated expansion of the universe, could play a role in the formation of such voids. Dark energy makes up most of the universe's total energy content, but its exact nature is still unknown. It's possible that dark energy could influence the way matter is distributed on a large scale, creating voids like the one in Eridanus. However, this theory is also speculative, and much more research is needed to determine whether dark energy could be responsible for the void's existence. A star with wildly inconsistent brightness. In the constellation Cygnus, over 1,400 light-years from Earth, there is a star that has captivated astronomers and the public alike. Its official name is KICE 8462852, but it is more commonly known as Tabby's star, named after the astronomer Tabitha Boyajian, who first brought attention to its unusual behavior. At first glance, it seems like any other star in the night sky, a distant point of light among billions of others. But what sets Tabby's star apart is its bizarre and inconsistent brightness, which flickers in ways that have baffled scientists since its discovery. Stars are generally stable, their brightness fluctuating only slightly over time. However, in 2015, researchers analyzing data from the Kepler Space Telescope noticed something unusual about Tabby's star. The light coming from it wasn't steady, and the dips in its brightness were far more dramatic and irregular than what is typically seen. Stars can dim temporarily if something passes in front of them, such as a planet or a cloud of dust. But the pattern of dimming observed with Tabby's star was unlike anything researchers had seen before. At times, the star's light would dim by as much as 22%, far more than could be explained by a planet or any other known object passing in front of it. This peculiar behavior led to a flurry of speculation and theories. The most sensational of these suggested the possibility of an alien megastructure, an enormous, artificially constructed object orbiting the star and periodically blocking its light. The idea captured the imagination of many, as it evoked images of vast spacefaring civilizations building colossal structures to harness the energy of their star. Known as a Dyson sphere, such a structure could theoretically be built by an advanced civilization to capture solar energy on a massive scale. If Tabby's star was being dimmed by such a megastructure, it would be the first evidence of intelligent life beyond Earth. However, the alien megastructure hypothesis, while captivating, remains highly speculative and has little supporting evidence. Extensive searches for radio signals or any other indicators of intelligent life have turned up nothing. Furthermore, the irregular pattern of dimming does not fit neatly into the idea of a solid orbiting structure. while the idea remains popular in science fiction circles, most scientists have turned their attention to more plausible explanations for Tabby's star's strange behavior. One of the leading theories is that the star's dimming is caused by swarms of comets or fragments of comets passing in front of it. According to this idea, a family of comets orbiting the star could occasionally block its light as they travel through space. These comets could be surrounded by clouds of gas and dust, which would help explain the irregularity of the dimming. Unlike planets, which follow predictable orbits and cause regular dips in a star's light, a swarm of comets could cause the star to dim in more chaotic and unpredictable ways. However, even this theory has its limitations. No direct evidence of such a comet swarm has been observed, and the amount of material needed to cause such significant dimming would have to be enormous. It's also possible that the dimming is caused by unusual forms of stellar dust. Dust particles in space can scatter and absorb light, causing a star's brightness to fluctuate. If there were large clouds of dust surrounding Tabby's star, this could account for the irregular dimming. Some researchers have suggested that the dust might come from the remnants of a disrupted planet or moon, which could have been torn apart by the star's gravity. As the dust moves in and out of our line of sight, it could block portions of the star's light, creating the strange patterns of brightness that have been observed. However, the properties of the dust would need to be quite different from typical interstellar dust to cause such dramatic dimming. There are also more exotic possibilities, including the idea that the dimming might be caused by internal processes within the star itself. Some researchers have proposed that Tabby's star might be undergoing a phase of stellar evolution that we do not fully understand, causing its brightness to fluctuate in unexpected ways. Stars can go through periods of instability as they age, and while Tabby's star does not fit the typical profile of a star in such a phase, it is possible that we are witnessing something entirely new. This would require a deeper understanding of stellar physics, as it would suggest that there are mechanisms at play within stars that we have not yet discovered. Despite the wide range of theories, there is no single explanation that fully accounts for the strange behavior of Tabby's star. Each hypothesis has its strengths and weaknesses, but none have been conclusively proven. The mystery remains, and with it comes a sense of excitement and curiosity. What could be causing a star to behave in such an unpredictable and unusual manner? Is it a natural phenomenon that we have yet to fully understand? Or is it something more extraordinary? In many ways, the mystery of Tabby's star reflects the broader challenges of astrophysics and space exploration. The universe is full of surprises, and as our technology improves and our ability to observe distant stars becomes more refined, we continue to encounter phenomena that defy our expectations. Tabby's star is a reminder that, despite centuries of scientific progress, there is still so much we do not know about the cosmos. It invites us to remain open to new possibilities and to approach the unknown with curiosity and wonder. Tabby's star has also sparked a renewed interest in citizen science. In fact, it was through the work of citizen scientists, ordinary people who help analyze astronomical data, that the star's unusual behavior was first noticed. Projects like Planet Hunters allow members of the public to sift through data from telescopes and identify potential exoplanets or other celestial phenomena. In the case of Tabby's star, it was citizen scientists who first flagged the irregular dimming, demonstrating the valuable role that non-professionals can play in scientific discovery. As the investigation into Tabby's star continues, it raises deeper philosophical questions about the nature of discovery and the limits of human understanding. What do we do when faced with a mystery that defies explanation? How do we balance skepticism with the excitement of potential breakthroughs? And in a universe as vast and complex as ours, how many other mysteries are waiting to be found, hidden in the distant light of faraway stars? Whether its strange behavior is the result of comets, dust, or some other unknown phenomenon, it stands as a reminder of the wonders that lie beyond our reach and the boundless curiosity that drives us to explore them. The Red Rectangle Nebula's geometry. In the distant reaches of space, most nebulae are a chaotic mix of gas and dust, spread across the sky in random swirling patterns. Their shapes are often irregular and amorphous, born out of the tumultuous forces at play in the cosmos. But nestled within the Milky Way, about 2,300 light-years from Earth, there is a nebula that defies this norm. Known as the Red Rectangle Nebula, it stands out not because of its color or its size, but because of its geometry, its eerie, almost impossible precision. Unlike the typical chaos of cosmic clouds, the Red Rectangle is unnervingly symmetrical, presenting a shape that has both puzzled and fascinated astronomers. The Red Rectangle Nebula gets its name from its unusual appearance. Seen from Earth, it resembles a glowing red X, with long parallel lines extending outward from the center. These lines form what looks like a perfect rectangle, a sharp and symmetrical structure that is rarely seen in the chaotic environment of space. At the center of this cosmic geometry is a binary star system, where two stars orbit around each other, and it is from this system that the nebula's light and structure seem to emanate. The sharpness and precision of the shape are striking, as if carved with purpose, a far cry from the random swirls and eddies we expect from nebulae. The Red Rectangle Nebula's symmetry has led scientists to speculate about the processes that could create such a unique and precise shape. One of the most widely accepted theories is that the nebula's geometry is a result of the binary star system at its center. As the two stars orbit each other, their gravitational forces interact in complex ways, shaping the surrounding gas and dust into the symmetrical pattern that we observe. The interaction between the two stars likely produces a series of outflows, jets of gas and dust, that are channeled into the nebula's distinctive rectangular form. Over time, these outflows create the parallel lines and sharp angles that define the red rectangle's appearance. But even with this explanation, the nebula's geometry remains puzzling. While binary star systems are known to create symmetrical structures in nebulae, the sharpness and regularity of the red rectangle are unusual. Most nebulae, even those influenced by binary stars, still exhibit some degree of randomness or irregularity in their shapes. The red rectangle, however, is different. Its lines are unnervingly straight, its angles sharp and precise, as if sculpted with intention. This level of symmetry is not something typically seen in cosmic structures, which are usually subject to the unpredictable forces of stellar winds, radiation, and turbulence. Adding to the mystery is the nebula's distinct color. The red rectangle glows with a deep reddish hue, which is likely caused by a combination of the gas and dust within the nebula and the light from the central stars. The red color may be the result of organic compounds called polycyclic aromatic hydrocarbons, PAHs, which are common in interstellar space and can produce reddish light when illuminated by stars. However, the exact composition of the nebula and the processes that give it its unique color are still not fully understood. The red rectangle's unusual geometry and color have prompted some researchers to explore more speculative ideas about its formation. Some have suggested that the sharpness of the nebula's shape could be influenced by magnetic fields, which might be channeling the gas and dust into the symmetrical pattern we observe. Others have proposed that the interaction between the two stars in the binary system is more complex than previously thought, involving processes that are not yet fully understood in stellar astrophysics. These ideas remain unproven, but they reflect the sense of wonder and curiosity that the red rectangle inspires. The central stars of the red rectangle are themselves an interesting system. The pair consists of an aging red giant and a smaller companion star, likely a white dwarf. As the red giant nears the end of its life, it sheds its outer layers of gas, creating the material that forms the nebula. This process is common in binary star systems, but in the case of the red rectangle, it seems to have produced a far more ordered and symmetrical structure than is usually seen. The outflows from the dying red giant are thought to be funneled into specific directions by the gravitational forces of the companion star, helping to shape the nebula into its distinctive rectangular form. The interaction between the two stars also creates a phenomenon known as a circumbinary disk, a disk of gas and dust that orbits around both stars. This disk is thought to play a key role in shaping the nebula's geometry, acting as a kind of sculptor that channels the outflows from the stars into the straight lines and sharp angles that define the red rectangle. The circumbinary disk is also responsible for reflecting the light from the stars, which illuminates the nebula and makes it visible to us. Despite these theories, many questions about the red rectangle remain unanswered. The nebula's geometry is so precise that it challenges our understanding of how such structures can form in the chaotic environment of space. Cosmic clouds of gas and dust are typically subject to a wide range of forces, stellar winds, radiation pressure, and turbulence, that tend to create more irregular shapes. The fact that the red rectangle has maintained such a high degree of symmetry over time is difficult to explain. It suggests that there may be additional factors at play in the formation of the nebula, factors that we do not yet fully understand. The red rectangle also raises broader questions about the nature of order and chaos in the universe. In a cosmos that is often defined by randomness and unpredictability, structures like the red rectangle stand out as exceptions. They challenge the assumption that cosmic phenomena must always be chaotic, suggesting that under the right conditions, order and symmetry can emerge even in the most turbulent environments. The nebula's precise geometry is a reminder that the universe is full of surprises and that there are still many mysteries to be uncovered. For astronomers, the red rectangle represents an opportunity to learn more about the complex processes that shape nebulae and other cosmic structures. By studying the nebula in greater detail, scientists hope to uncover new insights into the interactions between binary stars, the role of magnetic fields, and the forces that govern the behavior of gas and dust in space. Each new observation adds to our understanding, but the nebula's sharp lines and symmetrical form continue to defy easy explanation. Rogue planets, the wanderers of space. Most planets orbit stars, bound by gravity to the warm, glowing orbs that provide them with light and energy. This has long been the image we hold of planets, part of solar systems, circling their suns in predictable patterns. But not all planets fit this mold. Scattered throughout the cosmos are rogue planets, mysterious worlds that drift alone through space, unattached to any star. These planets, sometimes called orphan planets, wander the galaxy in cold isolation, offering a glimpse into a different kind of planetary existence. Rogue planets are not tethered to any solar system. They do not receive warmth or light from a nearby star, making them difficult to detect. These lonely wanderers could number in the billions, silently traveling through the galaxy, hidden in the dark. Their origins are a mystery. Some may have formed in solar systems, only to be ejected by the gravitational pull of larger planets or stars. Others might have formed on their own, directly from clouds of gas and dust, just like stars, but never grew large enough to ignite fusion and become stars themselves. Whatever their origins, these planets drift freely through the universe, cut off from the energy sources we typically associate with planetary life. The discovery of rogue planets has challenged many assumptions about planetary formation. In the traditional model, planets form from the leftover material surrounding a young star. As dust and gas in a protoplanetary disk begin to clump together, planets take shape, eventually settling into stable orbits around their parent stars. This process explains the orderly arrangement of planets in solar systems like our own. But rogue planets, unbound from any star, suggest that planetary formation might be more chaotic than previously thought. If planets can be ejected from their solar systems or form independently of stars, the process of planetary formation must be more complex and varied than the standard model suggests. One of the most intriguing questions surrounding rogue planets is whether they might be capable of supporting life. At first glance, this seems unlikely. Without a star to provide heat and light, these planets would be cold, dark places, their surfaces frozen solid. But beneath the icy exteriors of some rogue planets there could be a different story. Some scientists believed that these planets might harbor liquid oceans beneath their frozen surfaces, kept warm by the planet's own internal heat. Even without the warmth of a star, a rogue planet could generate heat through a process known as tidal heating. This occurs when gravitational forces stretch and squeeze a planet's interior, generating heat in the process. If a rogue planet has a moon, or if it passes near a star or other massive object during its journey through space, these gravitational interactions could produce enough internal heat to maintain liquid water beneath an icy crust. Additionally, the decay of radioactive elements in the planet's core could provide a steady source of warmth, further enhancing the possibility of liquid water. On Earth, life has been found in some of the most extreme environments, including deep beneath the ocean floor and in polar ice caps. These discoveries have expanded the definition of what scientists consider habitable. If life can thrive in such extreme conditions on Earth, could it also exist deep beneath the surface of a rogue planet, far from the light of any star? While this idea remains speculative, it raises the possibility that rogue planets might host microbial life forms, living in subsurface oceans heated by internal processes. The existence of rogue planets also prompts a rethinking of the requirements for life. For a long time, scientists believed that life could only exist in the habitable zone of a star system, the region around a star where temperatures are just right for liquid water to exist on a planet's surface. But rogue planets suggest that life might not need a star at all. Instead, a planet's internal heat could be sufficient to create and sustain environments where life could emerge and survive. This idea has broadened the search for life beyond our solar system, as it suggests that habitable worlds could exist even in the darkest, most remote corners of the galaxy. Detecting rogue planets is no easy task. Because they do not emit their own light and are not illuminated by a nearby star, they are nearly invisible to traditional telescopes. Instead, astronomers have to rely on indirect methods to find them. One such method is gravitational microlensing, a technique that takes advantage of the fact that massive objects bend light as it passes by them. When a rogue planet passes in front of a distant star, its gravity bends the star's light, creating a temporary brightening that can be detected by telescopes. This method has led to the discovery of several rogue planets, though many more are likely out there, waiting to be found. One of the most famous rogue planets discovered so far is known as CFBD SAR 2149-0403. This planet, located about 100 light-years from Earth, is a gas giant similar in size to Jupiter. It was detected using gravitational microlensing and stands as one of the few confirmed rogue planets. While it does not have the potential to support life as we know it, its discovery has provided valuable insights into the nature of rogue planets and how they can be detected. As our technology improves and we develop new methods for observing the universe, it is likely that we will discover many more rogue planets in the coming years. Some estimates suggest that there could be as many rogue planets as there are stars in the Milky Way galaxy, if not more. These wandering worlds could come in a wide variety of forms: rocky planets, gas giants, and even icy planets with subsurface oceans. The diversity of these planets could rival that of planets bound to stars, offering a new frontier for exploration and discovery. Hypervelocity stars. In the quiet, predictable movements of stars within a galaxy, there are certain patterns astronomers have come to expect. Stars follow their orbits around the galactic center at speeds that, while swift, are well within the range dictated by the galaxy's gravitational forces. However, scattered among these stars are outliers, rogue stars that defy the normal pace of galactic life. These are hypervelocity stars traveling at such extraordinary speeds that they can break free from the gravitational pull of their home galaxy, racing into the vast emptiness of intergalactic space. Hypervelocity stars are rare, and their discovery has shed new light on the extreme forces that can act on stars in the chaotic environments of galaxies. While most stars move at speeds of a few hundred kilometers per second within their galaxies, hypervelocity stars can reach speeds of over 1,000 kilometers per second, fast enough to escape the galaxy's gravitational grip. Once free, they continue their journey through the universe, destined to wander through the intergalactic void for eternity. The origin of these hypervelocity stars is a topic of great interest to astronomers. One of the most widely accepted theories is that these stars are ejected during close encounters with supermassive black holes, the massive objects that reside at the centers of most galaxies, including our own Milky Way. When a star ventures too close to a supermassive black hole, it can be caught in a complex gravitational interaction. In some cases, the intense gravitational forces can tear apart a binary star system, a system in which two stars orbit each other. One star might be pulled into the black hole, while the other is flung away at an incredible speed, becoming a hypervelocity star. This process is thought to occur near the supermassive black hole at the center of the Milky Way, known as Sagittarius A. The immense gravitational field of Sagittarius A can accelerate stars to extreme velocities during close encounters, sending them hurtling out of the galaxy. Once a star reaches a certain speed, known as the escape velocity, it can break free from the gravitational pull of the galaxy and continue traveling through space without being drawn back. For hypervelocity stars, this means a one-way trip out of the galaxy into the unknown expanses beyond. Another potential source of hypervelocity stars comes from gravitational interactions between galaxies. When galaxies collide or pass near each other, the gravitational forces involved can fling stars out at high speeds. In these complex interactions, a star might be accelerated to hypervelocity either during the collision itself or as a result of the gravitational influence of a nearby massive object, such as a supermassive black hole in the merging galaxy. These interactions can result in stars being ejected not only from their home galaxies, but also from the entire group of galaxies they belong to. Hypervelocity stars present a unique opportunity for scientists to study extreme astrophysical phenomena. Because they travel so fast and are typically moving away from their home galaxy, these stars can serve as probes of the outermost regions of galaxies and the space between them. By studying hypervelocity stars, astronomers can gain insights into the gravitational environments near supermassive black holes, the distribution of stars in the galactic halo, the outermost region of a galaxy, and the dynamics of galactic collisions. One of the first hypervelocity stars discovered, known as HVS-1, was found in 2005 by a team of astronomers using the MMT Observatory in Arizona. This star was traveling at a speed of over 700 kilometers per second, far faster than typical stars in the Milky Way. Its high velocity suggested that it had been ejected from the center of the galaxy, likely after a close encounter with Sagittarius A*. Since then, astronomers have identified dozens of hypervelocity stars, each with its own story of a violent past, flung into space by forces far beyond our everyday experience. The journey of a hypervelocity star is a lonely one. Once a star has been ejected from its galaxy, it is no longer bound by the familiar gravitational forces that keep most stars in stable orbits. Instead, it travels through the vast emptiness between galaxies, moving farther and farther away from its origin. These stars will eventually escape the gravitational influence of even the largest galactic structures and drift into intergalactic space, where they will continue their solitary journey for billions of years. The speed of hypervelocity stars also poses interesting questions about their ultimate fate. While most stars spend their lifetimes orbiting the centers of their galaxies, hypervelocity stars are effectively exiled from their stellar communities. Over time, they will leave the galactic halo and enter the largely empty space between galaxies, where the nearest neighbors are light years away. These stars are unlikely to encounter other objects as they travel, meaning that they may never interact with other stars or planets again. Their isolation is complete, and they will spend the remainder of their lives drifting through the universe, their origins a distant memory. While hypervelocity stars are fascinating in their own right, their discovery also raises broader questions about the dynamics of galaxies and the forces that govern the movements of stars. The existence of these high-speed stars suggests that the environments near supermassive black holes are far more dynamic and chaotic than previously thought. The fact that a star can be flung out of a galaxy at such extreme speeds speaks to the immense power of gravitational forces at play near black holes, where the normal rules of stellar motion can be dramatically altered. Hypervelocity stars also provide a glimpse into the larger processes that shape galaxies and the universe as a whole. The ejection of stars from galaxies, whether through interactions with black holes or galactic collisions, is a reminder that galaxies are not static, isolated structures. They are constantly interacting with each other and with the objects within them, creating a dynamic environment where stars can be born, destroyed, or sent hurtling into the depths of space. These interactions are part of the larger picture of galaxy evolution, a process that plays out over billions of years and shapes the structure of the universe. Despite their incredible speed, hypervelocity stars are difficult to detect. They are typically located in the outer regions of the galaxy, far from the dense clusters of stars near the galactic center, and they are often moving away from the Earth. This makes them faint and hard to spot with traditional telescopes. However, advances in astronomical technology, such as the use of large-scale sky surveys and high-precision instruments, have made it possible to identify these stars and track their movements. As more hypervelocity stars are discovered, astronomers hope to learn more about their origins and the forces that propel them on their high-speed journeys. Hoag's object. Galaxies come in all shapes and sizes, spirals, ellipticals, and irregular forms that stretch across the cosmos in complex patterns. But among this variety, one galaxy stands out for its striking symmetry and unusual structure: Hoag's object. Discovered in 1950 by astronomer Arthur Hoag, this peculiar galaxy defies the typical classifications that astronomers use to describe galactic forms. It is a nearly perfect ring of stars encircling a bright, spherical core, creating an almost otherworldly appearance that continues to fascinate and puzzle scientists. Hoag's object is a type of ring galaxy, a relatively rare formation in the universe, but its level of symmetry is unlike anything commonly observed. At first glance, the galaxy appears as though someone has drawn a perfect circle of stars surrounding a bright, dense core, with an empty region of space in between. The outer ring is made up of bright young blue stars, which shine against the darkness of space. In the center, the core consists of older, redder stars, characteristic of a much more mature stellar population. This sharp contrast between the bright young ring and the older core adds to the galaxy's mysterious and captivating appearance. What makes Hoag's object particularly intriguing is its near-perfect circular shape. Most galaxies, even ring galaxies, exhibit some degree of irregularity, spirals that are not quite even, rings that appear warped or off-center, or interactions with nearby galaxies that create distortions in their structure. But Hoag's object seems to defy this pattern. Its ring is smooth and symmetrical, its core neatly placed in the center, and there is no obvious sign of the galactic interactions or gravitational forces that typically produce such formations. This symmetry has left astronomers searching for an explanation. The formation of ring galaxies is usually associated with galactic collisions or interactions. When a smaller galaxy passes through a larger one, the gravitational forces involved can create ripples in the distribution of gas and stars, leading to the formation of a ring. This is similar to the way a stone dropped in water creates ripples that radiate outward. But in the case of Hoag's object, there is no evidence of a nearby galaxy that could have caused such an interaction. The galaxy sits in relative isolation, without the telltale signs of a past collision, such as distorted shapes or trailing streams of stars, that are often seen in galaxies that have undergone close encounters. One theory is that Hoag's object could be the result of a rare gravitational phenomenon, known as a resonant ring. In this scenario, the galaxy's core might have interacted with a smaller passing object long ago, but instead of a violent collision, the interaction could have been more subtle, creating a gravitational resonance that caused gas and stars to form a ring around the core. This would explain the nearly perfect symmetry of the galaxy, as the gravitational forces involved would have worked in a balanced, circular fashion. However, no direct evidence of such an event has been found, leaving this theory as one of many possibilities. Another idea is that Hoag's object could have formed through an internal process, where the outer ring is the result of a burst of star formation that occurred after the galaxy's core had already formed. In this model, the galaxy's core would have formed first, with older stars gradually aging and becoming redder, as we see in the central region. Later, a wave of gas could have moved outward from the core, triggering the formation of new, younger stars in a ring around the galaxy. This would explain the distinct separation between the older stars in the core and the younger stars in the ring, but it does not fully account for the galaxy's symmetry, which remains one of its most puzzling features. Adding to the mystery is the fact that Hoag's object is not entirely unique, though it is rare. Other ring galaxies have been observed, though few exhibit the same level of symmetry. Most other ring galaxies show signs of disruption or interaction with nearby objects, and their rings tend to be less perfectly circular. Hoag's object stands apart in this regard, as it appears almost undisturbed, as though it has maintained its form for billions of years without interference from other galaxies or external forces. Hoag's object also raises questions about the lifespan of ring galaxies. How long can a structure like this remain stable in the ever-changing dynamic environment of the universe? Will the ring eventually collapse inward, merging with the core, or will it continue to expand outward, dispersing into space? The lack of visible interactions with other galaxies suggests that Hoag's object has remained stable for a significant amount of time, but the exact mechanisms that keep it in such a perfect state are not fully understood. In the years since its discovery, astronomers have used increasingly advanced technology to study Hoag's object in greater detail. Observations with the Hubble Space Telescope have provided stunning images of the galaxy, revealing the intricate details of its structure. These observations have also revealed a surprising feature: a second, smaller ring galaxy lurking in the background, visible through the empty region between the core and the outer ring. This discovery adds an additional layer of mystery to Hoag's object, as it suggests that the galaxy may be part of a larger, more complex system of objects. Despite these advances, no consensus has been reached on the exact mechanisms that created Hoag's object. It remains one of the great puzzles of galactic formation, a reminder that even in a universe filled with billions of galaxies, there are still many phenomena that defy easy explanation. The galaxy's isolation and its perfect shape challenge existing models of how galaxies form and evolve, suggesting that there may be processes at work that we do not yet fully understand. For now, Hoag's object stands as a beautiful anomaly in the cosmos, a near-perfect circle of stars that continues to fascinate and perplex astronomers. Its unusual form invites us to reconsider the processes that shape the universe, reminding us that the cosmos is not always governed by the rules we expect. Antimatter annihilation in the galactic center. Deep within the heart of the Milky Way, a region shrouded in dust and gas, lies a source of intense and mysterious energy. Astronomers studying this galactic center have long observed a strange and persistent phenomenon: an unusual amount of gamma rays, the most energetic form of electromagnetic radiation, pouring out from this crowded region of space. These gamma rays are not simply the product of normal stellar activity. They appear to be linked to something far more exotic, something that suggests the presence of antimatter annihilation, a process where matter and antimatter collide, releasing immense energy in the form of gamma rays. Antimatter is the mirror opposite of ordinary matter. For every particle of matter, there exists an antimatter counterpart with the same mass, but an opposite electric charge. When a particle of matter meets its antimatter twin, they annihilate each other in a burst of energy, converting their mass into gamma rays. This process is highly efficient and releases enormous amounts of energy, far more than the energy released in typical nuclear reactions. The idea that antimatter could be responsible for the gamma rays coming from the center of our galaxy is both exciting and perplexing, as it hints at an unseen energetic world operating within the core of the Milky Way. The mystery lies not only in the gamma rays themselves, but also in the source of the antimatter. Under current theories of the universe, there simply shouldn't be enough antimatter present to create the volume of gamma rays that astronomers are observing. In the early universe, scientists believed that matter and antimatter were created in roughly equal amounts. But for reasons that are still not fully understood, most of the antimatter disappeared, leaving behind a universe dominated by matter. Today, antimatter is rare, and when it is produced, it quickly annihilates with matter, making it difficult to detect or accumulate in large quantities. Despite the apparent scarcity of antimatter, the center of the Milky Way seems to be producing enough of it to fuel these mysterious gamma-ray emissions. The source of this antimatter has puzzled scientists for decades, and several theories have been proposed to explain its presence. One possible explanation involves pulsars, which are highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation. Pulsars are known to be powerful sources of gamma rays, and some researchers have suggested that the antimatter annihilation observed in the galactic center could be the result of processes occurring in the magnetospheres of these pulsars. In this scenario, the intense magnetic fields around pulsars could be generating pairs of matter and antimatter particles, which then collide and annihilate, producing gamma rays in the process. This theory is supported by the fact that pulsars are common in the dense environments found near the center of galaxies, but it doesn't fully explain the scale of the gamma-ray emissions observed. Another possibility is that the antimatter is being produced by the supermassive black hole located at the very center of the Milky Way, known as Sagittarius A. Black holes are known to generate intense gravitational and electromagnetic fields, and the environment around Sagittarius A is highly energetic. Some scientists believe that the extreme conditions near this black hole could lead to the production of antimatter, which would then annihilate with matter in the surrounding region, generating the observed gamma rays. However, while black holes can certainly produce energetic events, the mechanics of how they would generate significant quantities of antimatter remain unclear. One of the more speculative ideas is that the gamma rays could be the result of dark matter interactions. Dark matter, an invisible substance that makes up about 85% of the universe's mass, does not interact with ordinary matter through electromagnetic forces, making it extremely difficult to detect. Some theories suggest that dark matter particles could annihilate with each other, producing gamma rays as a byproduct. If the center of the Milky Way contains a high concentration of dark matter, as some models predict, it could be that these particles are colliding and annihilating, releasing gamma rays in the process. This would provide a tantalizing link between the gamma ray emissions and the elusive dark matter that permeates the universe. However, dark matter remains one of the greatest mysteries in astrophysics, and there is no direct evidence yet to support this theory. Adding to the complexity of the situation is the fact that the galactic center is an extremely active and chaotic region. The density of stars, gas, and dust is far higher than in other parts of the galaxy, and the presence of Sagittarius A means that the gravitational forces at play are immense. This chaotic environment could be contributing to the production of antimatter in ways that we do not yet fully understand. The region is also home to a variety of high-energy processes, such as supernovae and stellar winds, which could be involved in the creation of antimatter and the subsequent annihilation events that produce gamma rays. Despite these theories, no single explanation has emerged as the definitive answer to the mystery of antimatter annihilation in the galactic center. Each proposed source, whether pulsars, black holes, or dark matter, has its own strengths and weaknesses, but none fully account for the scale and persistence of the gamma ray emissions observed. This leaves scientists with more questions than answers, and the search for the true source of this antimatter continues. What makes this puzzle even more intriguing is that it forces scientists to reconsider some of the fundamental assumptions about the universe. If large amounts of antimatter are being produced in the galactic center, it could suggest that our understanding of matter-antimatter asymmetry, one of the key unsolved problems in physics, is incomplete. the universe is overwhelmingly composed of matter, and the reasons for this imbalance between matter and antimatter are still unknown. The existence of significant antimatter production in the heart of our galaxy could provide new clues about this cosmic mystery. Additionally, the possibility that dark matter could be involved in these gamma-ray emissions raises important questions about the nature of dark matter itself. If dark matter particles are capable of annihilating each other and producing gamma rays, this would represent a breakthrough in our understanding of this invisible substance. Such a discovery would not only shed light on the processes occurring in the galactic center, but also provide critical insights into the fundamental nature of dark matter, which remains one of the most elusive components of the universe. The center of our galaxy is a place of extremes: extreme gravity, extreme density, and extreme energy. It is a region where the usual rules of astrophysics often give way to more exotic processes, and the presence of antimatter annihilation only adds to the sense of mystery. Whether the gamma rays are the result of pulsars, black holes, dark matter, or something entirely unexpected, they offer a window into the most energetic and dynamic parts of the Milky Way. Blue stragglers. In the quiet, aging star clusters scattered throughout the universe, the stars follow a predictable life cycle. Over millions or billions of years, they burn through their fuel, gradually fading, cooling, and growing older. Most stars in these ancient clusters are at advanced stages of their lives, showing signs of slow decay. But among these older stars, astronomers have noticed something strange. There are a few stars that seem out of place. These stars, known as blue stragglers, shine brightly with a hot blue light that suggests they are much younger than the rest of the stars around them. Their presence in these old star clusters poses a mystery, one that challenges our understanding of stellar evolution. Blue stragglers are so named because they appear to straggle behind in the aging process. While most stars in a given cluster are aging in predictable ways, cooling and growing dimmer over time, blue stragglers stand out by remaining bright, hot, and blue, a color associated with younger, more massive stars. They seem to defy the natural progression of stellar aging, as if they've somehow managed to rewind the clock and regain their youthful vigor. The question that has puzzled astronomers since their discovery in the 1950s is, how did these stars, which should have aged along with their neighbors, end up looking so much younger? The prevailing theory to explain the existence of blue stragglers is that they are the result of stellar collisions or mergers. In this scenario, two stars in a dense star cluster could collide, or one star might draw material from a companion star, causing them to combine their mass. When this happens, the resulting star can gain enough new fuel, primarily hydrogen, to reignite and burn hotter and brighter than before. This process effectively rejuvenates the star, giving it a second lease on life and allowing it to shine with the intense blue light typically seen in younger stars. One way this could happen is through a process called mass transfer, where one star in a binary system, a system in which two stars orbit each other, gradually pulls material from its companion star. As the first star accumulates more hydrogen, it becomes more massive and starts to burn hotter, while the companion star gradually loses its mass. In such cases, the blue straggler appears younger because it has been refueled by the additional hydrogen, allowing it to extend its lifespan and appear much younger than its actual age. The donor star, meanwhile, often becomes a dim, small remnant, like a white dwarf, after it has lost much of its mass. It is also possible that blue stragglers form when two stars physically collide and merge into a single, larger star. This kind of event is more likely to happen in dense star clusters, where stars are packed closely together, increasing the chances of collisions. When two stars merge, the combined mass creates a new, more massive star that can burn hotter and brighter than either of the original stars. The newly formed blue straggler, despite being made from two older stars, appears younger because of its new mass and energy. Both of these mechanisms, mass transfer and stellar collisions, provide plausible explanations for the formation of blue stragglers, but they are not without their challenges. For one, not all blue stragglers seem to fit neatly into these categories. In some cases, astronomers have found blue stragglers that do not appear to be part of binary systems, raising questions about how these stars could have rejuvenated without a companion star to provide additional fuel. Additionally, while stellar collisions are more likely to occur in dense star clusters, they are still relatively rare events, making it unclear whether collisions alone can account for the number of blue stragglers observed. The exact mechanisms behind the formation of blue stragglers remain a topic of ongoing research. In recent years, astronomers have used more sophisticated tools such as space telescopes and advanced computer models to study these enigmatic stars in greater detail. By observing the motions, brightness, and spectral characteristics of blue stragglers, scientists are hoping to uncover more clues about their origins. One of the key challenges is determining whether a particular blue straggler formed through mass transfer or a collision, or whether there might be other, as yet undiscovered processes at play. Despite the uncertainties surrounding their formation, blue stragglers offer valuable insights into the dynamics of star clusters and the life cycles of stars. Star clusters are some of the oldest structures in the universe, and they serve as natural laboratories for studying stellar evolution. Most stars in these clusters follow predictable paths, evolving from hot, young stars into cooler, older ones as they burn through their fuel. Blue stragglers, however, break this pattern, offering a glimpse into the more chaotic and unpredictable aspects of stellar life. The presence of blue stragglers in a star cluster can also provide information about the cluster's age and history. Because blue stragglers are thought to form through interactions between stars, their abundance can indicate how densely packed the cluster is, and how frequently stars are likely to collide or transfer mass. In clusters where blue stragglers are more common, it suggests that stellar interactions play a significant role in shaping the cluster's evolution. Conversely, in clusters with fewer blue stragglers, it may indicate that stellar collisions and interactions are less frequent, or that the conditions for forming blue stragglers are less favorable. One of the most famous examples of blue stragglers is found in the globular cluster M3, a densely packed cluster of stars located about 33,900 light-years from Earth. M3 is home to hundreds of thousands of stars, most of which are older and in the later stages of their lives. However, scattered among these aging stars are dozens of blue stragglers, shining brightly and defying the cluster's overall age. Astronomers have studied M3 extensively, and it has become one of the key sites for understanding blue straggler formation. The cluster's high density makes it a prime candidate for stellar collisions, and many of the blue stragglers in M3 are thought to have formed through this process. While blue stragglers were first discovered in dense globular clusters like M3, they have since been found in a wide variety of environments, including open star clusters and even the galactic field, where stars are more spread out. The discovery of blue stragglers in these less dense environments has further complicated the picture, suggesting that the mechanisms behind their formation may be more diverse than originally thought. In these less crowded regions, stellar collisions are much less likely, leading some astronomers to propose alternative explanations for how blue stragglers form outside of dense clusters. The study of blue stragglers also touches on broader questions about the nature of stellar evolution and the forces that shape the universe. In many ways, these stars represent the idea that stellar life is not as linear or predictable as we once thought. While most stars follow a well-understood sequence from birth to death, blue stragglers show that there can be exceptions. Stars that are rejuvenated, reborn, or altered by interactions with their neighbors. These interactions can breathe new life into stars that would otherwise be on their way to cooling and fading, demonstrating the dynamic and interconnected nature of the universe. Planck time, the smallest possible unit of time. In the realm of physics, time is something we tend to think of as a continuous, ever-flowing river, measured in seconds, minutes, hours, and so on. We structure our entire understanding of the universe around it. But when you delve into the deepest levels of theoretical physics, down to the very fabric of space and time itself, there exists a concept so abstract and removed from everyday experience that it challenges our understanding of what time really is. This concept is called Planck time, the smallest possible unit of time that could exist, a fleeting moment so brief that it is beyond anything we can imagine or measure. Planck time is named after the German physicist Max Planck, one of the founding figures of quantum theory. In the early 20th century, Planck sought to develop a system of units based on fundamental constants of nature. Units that would be universal and not reliant on human-made systems like the metric or imperial systems. From this work, he derived the concept of Planck time, along with other fundamental units like Planck length and Planck energy. These units are not just mathematical curiosities. They represent the limits of our current understanding of the universe. To grasp how small Planck time is, consider this. 1 unit of Planck time is about 5.39 times 10 to the power of minus 44 seconds. This number is so minuscule that it defies. It is the amount of time it would take for light, the fastest thing in the universe, to travel a distance equal to 1 Planck length, which is about 1.6 times 10 to the power of minus 35 meters, itself an unimaginably small distance. At this scale, the familiar rules of classical physics no longer apply. Instead, the universe is governed by the strange and unpredictable laws of quantum mechanics. In Planck time, the universe exists at a threshold where quantum effects and gravity, the force that governs the large-scale structure of the universe, become equally important. This is a regime where the very fabric of space and time becomes uncertain, a state where the smooth, continuous spacetime described by Einstein's theory of relativity breaks down. Quantum gravity, a theoretical framework that scientists have yet to fully develop, is thought to dominate at this scale. It's a world where particles and fields behave in ways that are entirely unfamiliar to our everyday experience, and where the concept of time as we know it starts to lose its meaning. The importance of Planck time becomes even more pronounced when we think about the origins of the universe itself. According to the Big Bang theory, the universe began as an incredibly hot, dense point that rapidly expanded. But what happened in the first moments of the universe before this expansion? Physicists believe that in the earliest instance after the Big Bang, the universe existed in a state so extreme that our current theories of physics can't describe it. This period of time, often referred to as the Planck era, is believed to have lasted for only a few Planck times. During this brief epoch, the universe would have been governed entirely by quantum effects, with space, time, and matter all existing in a state of pure uncertainty. Because Planck time is so small, and the conditions of the universe during the Planck era were so extreme, it's impossible for us to observe or measure this early period directly. Theoretical physicists can only speculate about what the universe might have looked like at this scale. Some propose that space and time themselves were not yet fully formed, that they existed in a kind of quantum foam, a turbulent sea of fleeting, fluctuating particles and energies. In this picture, the universe would have been fundamentally different from anything we can currently observe or experience, a place where the conventional rules of cause and effect break down. The notion of time itself becomes slippery at this level. In our everyday world, time seems to move forward in a continuous flow. We experience seconds, minutes, and hours in a steady progression. But at the scale of Planck time, the idea of continuous time may not hold. Some physicists suggest that time might be quantized, meaning that it could exist in discrete chunks or intervals, much like matter is composed of atoms. If time is quantized, then Planck time would represent the smallest possible unit of time, the shortest duration that could have any physical meaning. Between these discrete moments, time as we understand it might not exist at all. This brings up profound philosophical questions about the nature of time itself. Is time something that exists independently, flowing on its own? Or is it merely a tool we use to describe the sequence of events? Does the universe have a clock that ticks away in Planck units? Or is time an artificial construct, a human invention that doesn't exist at the deepest levels of reality? In classical physics, time is often treated as an absolute, something that ticks away uniformly and independently of the events happening within the universe. But relativity complicates this picture. According to Einstein's theory of general relativity, time is not a fixed backdrop, but a dynamic, flexible dimension that is affected by gravity and the motion of objects. time can slow down near massive objects like black holes or for observers moving at extremely high speeds. In this view, time is part of the fabric of space itself, what we call space-time, and is deeply intertwined with the physical universe. At the scale of Planck time, though, even this picture of time breaks down. Space-time itself becomes subject to quantum uncertainties, and the smooth, continuous flow of time described by relativity gives way to something far more chaotic and uncertain. Some theories suggest that time might not even exist at the quantum level, that what we perceive as the flow of time is an emergent property that arises only at larger scales, where the effects of quantum uncertainty are smoothed out. In this view, time might not be a fundamental aspect of the universe at all, but rather a byproduct of the way we observe and interact with the world. If time is not fundamental, then the concept of Planck time might represent the smallest unit of change or interaction, rather than a literal tick of a cosmic clock. At this level, events might occur in discrete quantized steps with no continuous progression between them. The idea of time as a smooth, flowing dimension could be an illusion, a useful tool for describing the macroscopic world, but one that doesn't apply at the deepest levels of reality. This idea challenges our most basic intuitions about time and the universe. For most of human history, time has been seen as an absolute, something that exists independently of the events happening within it. But the discovery of Planck time and the insights of quantum mechanics and relativity suggest that time might be far more complex and fluid than we once thought. While we may never be able to directly observe the universe at the scale of Planck time, the concept continues to shape our understanding of the cosmos. It pushes the boundaries of physics and philosophy, forcing us to confront the limits of our knowledge and to consider possibilities that are far removed from our everyday experience. Planck time represents the point where our current theories of physics break down, where the universe becomes a place of pure uncertainty, governed by laws we have yet to fully understand. In the quest to unlock the mysteries of Planck time and the earliest moments of the universe, physicists are searching for a theory of quantum gravity, a framework that would unite the principles of quantum mechanics with general relativity. Such a theory could provide the tools needed to describe what happens at the scale of Planck time and offer deeper insights into the nature of space, time, and the universe itself. But until that day comes, Planck time remains an enigma, a reminder of the limits of human understanding and the vastness of the unknown. I hope you enjoyed this video. If you did, feel free to subscribe. Thank you for watching.